Hi, this is an example problem about a simple magnifying glass from chapter 26. Pause for a moment to read the question. Okay, to understand how a simple magnifying glass works, let's go look at a PDF real quick with some information here. First thing to note is that the magnification that we use for simple magnifying glass is not the same as the magnification we used when we did lenses and mirrors earlier. This is a capital M, and that's the ratio between two angles. And you can kind of see it in the picture. If you have an object and you look at it with your eye, the length of the object produces a certain angle above the optical axis here. And that's going to produce a certain angle of size image on your retina. If we use a magnifying glass, we use a converging lens, and that allows us to move the object closer to the eye. And so now you get a larger angle, and you get a larger angle on the image on your retina. What does the magnifying glass do? Well, you move that object closer, it produces a virtual image, which is going to be large. And so this is what's giving us that magnification. In any case, M comes from those pictures, and we can use this equation here to calculate it. It depends on three things: the focal length of the converging lens, the distance of the image, and the near point of the person's eye. Sign conventions are important here. N is positive, F, converging lens, is positive, but the image is virtual, so DI is negative. Let's copy these and we'll use these as we solve the problem here. So we'll refer to these. And well, this is a problem that is very similar to just any type of lens problem. It's got a single converging lens, right? So let's go ahead and draw a picture of this. Here's your principal axis. And let's go ahead and draw our converging lens here. Here's the lens. Here's your magnifying glass. Let's go ahead and draw the center of that lens. We'll use that to measure distances. And now we can go ahead and label some of the points here. So we've got a 5 centimeter focal point. So maybe around here. And that's going to give us a focal length here from the edge of the lens. So we can go ahead and write this as our focal point F. And our focal length here, little f, it's going to be 5 centimeters. Now we're going to assume in this case that the eyeball is kind of just right up here, right next to the lens. And it's a small distance from the magnifying glass compared to where the near point is. Near point is going to be way out here somewhere. N. And that's going to be 40 centimeters, okay? Now in part A, it says the image is at the jeweler's near point, maximum eye strain. So in the very first part, we're going to go ahead and stick our image right here. And so if we measure that from the lens out to the image, we get a value here that's equal to the near point. DI, we know that that's 40 centimeters. But what do the sign conventions tell us? DI is being virtual, so it's to be negative, right? Just like F was positive, converging lens. So we've got the information to be able to do part A here. We're going to use the equation there for the angular magnification. It's going to be equal to 1 divided by F. So 1 over F in this case, 1 over 5 centimeters, minus 1 divided by DI. That's going to be a negative 40 centimeters, all multiplied by the near point, a positive 40 centimeters. Putting that into the calculator, we get a value of 9. So the angular magnification in part A is 9. Let's look at part B. In part B, it asks, what is the angular magnification of the diamond when the jeweler views the image at his far point with unstrained eyes? So to be able to view that virtual image at the near point, that requires the jeweler to strain the ciliary muscles to create a lot of bending in the eye. That's a lot of strain, and you can actually relax your eye, and you'll be able to move this image out to infinity. So for part B, we're actually going to go ahead and, so here's part A, right? Part B, we're going to go ahead and move this image way the heck out here to infinity. So di, part B, minus infinity. And we can calculate that. So the angular magnification for part B, again, 1 over f, 1 over 5 centimeters, minus 1 over, it's a negative infinity, times 40 centimeters. And of course, 1 divided by infinity or negative infinity, this is just 0. That simplifies a bit. 40 centimeters divided by 5 centimeters comes out to be 8 in this case. So we end up getting a value of the angular magnification that's a little bit less if you want to relax your eyes. But if you're going to jeweler, you're going to be looking at a lot of this stuff for a long time, probably a good idea. Part C asks us, determine where the object is located in part A and in part B. So for part C, let's do the part A one first. This is just now going to be a straightforward thin lens equation because we have a lens and we have a image and a focal length. We can figure out where the object is, right? So remember that 1 over do plus 1 over di is equal to 1 over f. We know what f is, we know what di. Let's just calculate what do is here. So for this first part, we're going to go ahead and solve for 1 over do. It's equal to 1 over f minus 1 over di. That's 1 over 5 centimeters minus 1 over a negative 40 centimeters for part A, which gives us a value, a 0.225 centimeters. And when we calculate that, take the reciprocal, sorry, that's inverse centimeters, right? And take the reciprocal of that, we're going to get do is equal to 4.44 centimeters. So for part A, we've got the object is going to be, it's going to be about right there or so, right? There's part A. And remember, when you get things close to the focal point, that's when you get large magnification. So that's what's going on here. Close to the focal point, inside the focal point, giving you a large virtual image. Let's do the same thing for part B. So for part B, again, we're going to do the exact same thing. Now we're just going to change the value of the focal length, right? So we can take this exact same set of things here. We want to calculate what do is. We got to change this. No longer minus 40. Now it's minus infinity. So this whole thing is 0. And we can see 1 over do equals 1 over 5 centimeters, right? Which means that do in part B is just equal to 5 centimeters. And so in that case, we've kind of just moved the object over right up to the focal point, essentially, right here in part B. And that actually gives us a little bit less angular magnification, but allows us to reduce the strain on our eyes. There's your objects.